Welcome to Maths with EJD. In this video, I'll start talking about hyperbolic functions. And to start with, let's do an introduction to hyperbolic functions. Of course, if you have not subscribed to this channel, you want to do that so that you will not miss out on anything that is going on here. So subscribe to the channel, hit the notification bell so you can always get alerted when a new video is released. And of course, comment, like, and share. Okay, so hyperbolic functions are analogs. They are analogs of trigonometric functions. So it means they are comparable to trigonometric functions. I have a whole playlist on trigonometric functions. You can check for that playlist. We have up to 10 videos, I believe. So that can give you a foundation for this. So hyperbolic functions are analogs of trigonometric functions, but are related. They are related to hyperbolas. They are related to hyperbolas rather than circles. So it means trigonometric functions are related to circles, while hyperbolic functions are related to hyperbolas. That's why they are hyperbolic. Okay. Then it is important to also know that hyperbolic functions, that is, they arise naturally. They arise naturally in various areas of mathematics. So hyperbolic functions arise in various areas of mathematics, including geometry, calculus, and complex analysis, Okay, so the hyperbolic sign, you already know they are analogous to trigonometric functions. And then we have sine, cosine, tangent. And of course, we have their reciprocals. For sine, that will be cosecant. For cosine, that is secant. And for tangent, that is cotangent. So the hyperbolic sine and cosine functions are defined in terms of exponential functions. Okay, those are like the two foundational hyperbolic functions. So if we talk about the hyperbolic sine, which is written as sine, that's hyperbolic sine. So we have that as sine x is equal to e raised power x minus e raised power minus x divided by 2. That is what hyperbolic sine is. So this function represents the difference between the positive and negative exponential functions. The difference between the positive and negative exponential functions divided by 2. So the key word here is difference. It's difference, because that is how it is different from hyperbolic cosine. So let's see what hyperbolic cosine looks like. So talking about hyperbolic cosine, which is rendered as cos, so that is given as cos x, which is equal to e raised power x plus e raised power minus x divided by 2. So you see, in the other case, it is e raised power x minus e raised power minus x. Here it is e raised power x plus e raised power minus x divided by 2. So for sine is minus while cosine is plus. That's basically the difference. So in this other case, right, this function represents the sum of the positive and negative exponential functions and negative exponential functions divided by 2. So the two of them are basically about positive and negative exponential functions. So sine is the difference between positive and negative exponential function divided by 2, while cos is positive and negative, the sum of positive and negative exponential function divided by 2. So here, like I said before, the key word here is the sum for cos. Okay, so we need to know that these functions are essential. These functions are essential in describing shapes and phenomena that occur in hyperbolic geometry. That's related to hyperbola, right? Hyperbolic geometry and various physical contexts Okay, this is the point where I like to change all the markers. So let us go, and then we have, say, what haven't we used before? Okay, let me choose this. All right, so let's go for, so we've talked about introduction, right? We have an introduction to hyperbolic functions. So let's talk about the properties and graphs of hyperbolic functions. So properties and graphs of hyperbolic functions, functions. Or this is what I've been doing. Okay, so the first thing we'll be looking at will be of course, we'll be considering some notations and key properties. So let's start with the standard notation. Standard notation. Of course, we've talked about this already in a way. So the hyperbolic sign and cosine are denoted as sine x and cos x respectively. So we've seen that we have talked about that already. So that is the standard notation. So let's talk about the fundamental identity that we will come across here. Fundamental identity of hyperbolic functions. So one of the most important identities one of the most important identities involving hyperbolic functions, is this. That is cos squared x minus sine squared x equals 1. So we'll come across this a lot as far as we talk about hyperbolic functions. So this identity is analogous to the trigonometric identity, identity, which is cos squared x plus sine squared x is equal to 1. So this is a popular identity when you talk about trig. The only thing is that but with a key difference in sign, or with a key difference in sign, like that. Okay. So having done that, let's talk about the graphs of sine and cos. Graphs of sine and cos. Graphs of sine x and cos x. So, well, first of all, talking about sine x, the hyperbolic sine function, the hyperbolic sine function, which is sine x, is an odd function, Okay. What that simply means is that f of minus x is equal to minus f of x. That is what an odd function is. So if you put the negative of a particular value, the answer you get is the negative of the function expressed at that value. For instance, a very good odd function is x cubed. So if you put minus 2 into x cubed, the answer is, I'm talking about, let's just come by the way, you have f of x equals x cubed. So if you put f of minus 2, that is minus 2 raised to power 3. And that is the same thing as minus 2 times minus 2 times minus 2, that is minus 8. So you see, at the end of the day, f of minus 2 is the same thing as minus f of 2. So if you put 2 here, you get 8. So that's how you know an odd function. So we are going to contrast that with even function very soon when we get to sine. So it is an odd function, right? This is the meaning of what an odd function is. It is an odd function, meaning it is symmetric with respect to the origin. So because it is an odd function, so the meaning is that it is symmetric. It is symmetric with respect to the origin. With respect to the origin. Okay. And then the graph of sine x, the graph of sine x passes through the origin. It passes through the origin and exhibits exponential growth exhibits exponential growth as x moves away from 0. So that is, it is positive for x greater than 0. So as x is moving away from 0 on the positive side, the function will be positive, and it is negative as x is less than 0. Okay, so let's switch over to Desmos to see what sine x looks like. So So yeah, Desmos is a very good tool for visualizing graphs. So I just say sine x. Okay, so you can see the line jumps right out. So you can see that it passes through the origin 0, and then as x increases like this, you can see that the line, the red line here keeps increasing. So that is the exponential growth on the negative side. On the positive side, so as x is increasing that way, so you see that that line is also growing like that. So this is what we mean by, so it grows exponentially, and it's positive as x is greater than 0, negative as x is less than 0. So that's what that description is about. Okay. So that is the graph of sine x. Let's talk about cosh. Let's talk about cosh. Um, so now, so this is sine x here. So talking about cosh x. So the hyperbolic cosine function, the hyperbolic cosine function, which is cosh x, is an even function. It's an even function. So being an even function, that simply means that f of minus x is the same thing as f of x. So a very good example of an even function is, say, f of x equals x squared. So if you have f of minus 2, you have minus 2 raised to power 2, and the answer is 4. So if you have f of 2 also, the answer is still 2 raised to power 2, which is 4. So you see that here, f of minus 2 is the same thing as f of 2. So that is what an even function is. So cosh is actually an even function according to what its behavior, right? So it is an even function, and what that means is that it means that it is symmetric. It is symmetric with respect to the y-axis, Okay, so the graph of cosh x, does not pass through the origin. It does not pass through the origin, but has a minimum value. It has a minimum value 1. It has a minimum value of 1 at x is equal to 0. So again, the function exhibits exponential growth as x increases in either direction. So whether to the right or to the left, the function experiences exponential growth. So let's go back to Desmos and see what cosh looks like. So now we're here. So I mean, the red one is sine. So you can see this red tells you sine is red. Okay. So for cosh now, just say cosh x. Now you can see that. So as x is increasing on both positive and negative side, the function is growing exponentially, and it keeps growing like that. But then you see that when x is equal to 0, the value is at 1. And of course, that's easily understandable, right? From the very expression, cosh x is e raised to power x plus e raised to power minus x divided by 2. So when x is 0, so you have e raised to power 0 plus e raised to power minus 0, which is 1 plus 1, which is 2 divided by 2, and that's 1. So that's why the minimum value is actually 1, like that. So that is the graph of cosh x. So the next thing we want to talk about is, let's talk about the key features here, the key features of this. Key features. So you can see we've always talked about exponential growth. So key features. So first of all, we've always talked about exponential growth. Exponential growth. Both of them have exponential growth. So both functions show exponential behavior. Both functions show exponential behavior. Exponential behavior is that fact that the lines keep increasing in one way or the other. So both functions show exponential behavior for large values, of the absolute value of x, whether it is positive or negative. That's why we have absolute value of x. So both to the positive and negative side, they both have exponential growth. So remember, for sine x, it's something like this. For sine x, you have something coming, enters here, and it keeps growing the other way. Whereas for cos, it's something like this. So at x equals 0, so this is the minimum, then it comes and keeps growing on both sides. So that's the idea of exponential growth. Okay. So however, right? However, cos x grows faster. So you can say cos x grows faster because it involves a sum of exponentials. Because you're adding exponentials together, the growth for cos x will be faster than that of sin x, because that one is different. So it's a difference of exponential. So it involves a sum of exponentials, while sin x involves their difference. Okay. So that's one characteristic we see. Then we also see the idea of symmetry. See the idea of symmetry running there. Symmetry. Symmetry is more like equal. So when you divide the graph into two equal parts, so you have the same shape on both sides, though they may not be in the same direction. So symmetry, you see that sin x is symmetric. It is symmetric about the origin. It is symmetric about the origin. So this is what that simply means. So you have the curve like this, right? So you have this coming. And then it goes. So the shape here is the shape down here. That is what we mean by symmetricity. So sin x is symmetric about the origin. Sin x is symmetric about the origin, whereas okay, I guess I want to remove the graph first. So sin x is symmetric about the origin, while cos x is symmetric about the y-axis. Symmetric about the y-axis. And that is easy to comprehend because this is it. So you have this. So for sine, you have something coming, enters here, and goes this way. So this is sine x. Whereas cos x is like this. You have this, then the minimum is 1. So it's increasing this way. That this exponential growth. So this is the exponential growth for sine, and the one for sine down and up. So of course, this is the origin. So it has exponential growth, and it is also symmetric about. So if you divide it, it's divided into 2 by this point. So the shape you have on this side is like the same at this other side. That is what symmetricity is about. Okay, so let's talk next about comparison and applications. How do we compare these functions, and what are the applications? So let's compare them with trigonometric functions. Okay, first of all, we just say comparison, and applications, comparison and applications. Okay, so first of all, let's talk about comparison with trigonometric functions, with trigonometric functions. So first of all, what are the similarities? What similarities do they have? Similarities. What are the similarities between hyperbolic and trigonometric functions? First of all, just as sine x and cos x are related to limit circles, are related to the unit circle, sine x and cos x are related. They are related to the unit hyperbola, which is given as x squared minus y squared equals 1. Interestingly, the unit circle is given as x squared plus y squared equals 1. Okay, that's one thing. So that's one area. Another area is that both sets of functions, meaning sine x, cos x, sine x, cos x. So both sets of functions satisfy similar identities. Such as cos squared x minus sine squared x equals 1. This is for the hyperbolic functions. Then, and cos squared x plus sine squared x equals 1. This is for the trigonometric functions. Okay. So that's in terms of similarities. So let's talk about their differences now. Differences. Okay. The trigonometric functions, functions are periodic. They are periodic. And that means that they are repeating their value. So repeating their values over intervals of 2 pi, while hyperbolic functions are not periodic. They are not periodic. Okay. Again, trigonometric functions are bounded. Trigonometric functions are bounded. They are bounded, meaning their values are confined. Their values are confined to a certain range, E.g., you see that, of course, I'm going to show the graph again. -1 is less than or equal to sine x, less than or equal to 1. That simply means that sine x is always is bounded between -1 and 1, as we're going to see the graph very soon. So while hyperbolic functions grow exponentially, without bound, without bound. So you can say that trigonometric functions are bounded while hyperbolic functions are boundless. Okay, let's quickly visualize. Let's compare them graphically, going back to Desmos now. Okay, starting afresh, let's see sine x. Look at sine x. So you can see the boundedness, right? Sine x is always restrained between, so you see this is 1 and this is -1. So you can see that sine x is always, first of all, it is periodic within that limit. So it keeps going up and down, but then it doesn't go above 1, neither does it go below -1. So that's the sine x. But look at sine x now. Sine x. So see, oh, okay, sorry, I still do the same thing. Look at sine x. So you see sine x now, so it's growing exponentially, comes into this place, and then it keeps increasing. So it's not bounded. It's not bounded like that. So it's boundless, as we said. So now that is for sine x and sine x. Let's look at cos x and cos x. So cos x. See what cos x looks like. So cos x is also bounded between 1 and -1. So, of course, what's the difference between sine and cos? Sine passes through the origin. You can see sine is passing through the origin, but cos doesn't pass through the origin. So that's the difference. But they're both bounded between 1. So let's see what cos looks like. You already know what cos looks like. It's that like a bowl, So where's cos x, the highest level of cos x is the smallest level for cos x, as you can see. So because the minimum value of cos x is 1, and then it increases exponentially, on both sides. So that's a very nice comparison between trigonometric and hyperbolic functions. Okay, so let's come to the last part of this. Let's look at the last part, and that will be about the applications and significance of hyperbolic functions. Applications and significance of hyperbolic functions. Okay. Yeah, so first of all, in mathematics, what happens here? Hyperbolic functions appear in the solutions of linear differential equations. Especially those with constant coefficients. They are also used in calculus, particularly in evaluating certain integrals. In fact, that's the integrals of this type, integral of dx all over x squared plus a squared. So you need to use hyperbolic function to evaluate this kind of integral generally. Okay, so that's in mathematics. So let's talk about physics. How do we use hyperbolic functions in physics? In physics, the shape of a hanging cable, the shape of a hanging cable, the shape of a hanging cable or chain, the shape of a hanging cable or chain, which is called a catenary, is described by the hyperbolic cosine function, the hyperbolic cosine function. Also, hyperbolic functions are also used in special relativity, and in the description of rapidity, So that's one use and significance of hyperbolic functions in physics. So let's move to engineering. So for engineering now, hyperbolic functions are used in the analysis of electrical circuits. The analysis of electrical circuits, signal processing, and control theory, Okay, lastly, let's talk about the significance of hyperbolic functions in hyperbolic geometry. Okay, so in hyperbolic geometry, which deals with surfaces, of constant negative curvature. Hyperbolic functions play a central role, analogous to the role of trigonometric functions in Euclidean geometry. So you see, we are always drawing parallels between hyperbolic functions and trigonometric functions. So with this, we've come to the end of this video. If you have not subscribed, be sure to do that. Of course, hit the notification bell so you can always get alerted each time a new video is released. Then always like, comment, and share so that more people can have access to this wealth of knowledge. Thanks for always stopping by. See you next time. Bye.